Good afternoon, everyone, and welcome to reInvent 2024. Today, you're going to be attending our session about discovering emerging threats in cloud security. My name is Catherine Watkins.
And my name is Will Bowditch. So let's get started.
Great. So I'm going to start off with something that we all know and love, the shared responsibility model. And I know some of you are going to say, I've heard this story before, and I promise it's about to get much more interesting. But I want to recall the way that Amazon operates with its customers using the shared responsibility model. The shared responsibility model has two components. The first is the security of the cloud, where AWS is responsible for protecting the infrastructure that runs all of the services offered in the AWS Cloud. And the second piece is where customers have the responsibility for maintaining proper configurations and operations of their cloud services, and we call this security in the cloud. In our session today, we are going to share insights in the ways that engineering teams from within AWS are building protections that benefit all customers. And we're going to be pulling back the curtain and sharing the way that we are raising the bar of the security of the cloud on behalf of our customers. So first, a bit about myself. My name is Catherine Watkins, and I am a senior data scientist at AWS Security. I've been with AWS Security for just short of 5 great years, and I'm a member of a team called Sonaris. So you're probably wondering, what is this Sonaris thing, and how does it fit into AWS Security? So Sonaris lives within AWS Security, but this is an exciting moment for me because this is the very first time I get to talk with you as customers about what happens within our organization. We operate behind the scenes on behalf of customers, but today I get to share a bit about what happens from within AWS Security to protect both the cloud and you as customers. But you can see on the slide here that there's many different aspects to AWS Security. It covers everything from physical security to vulnerability management and compliance. But my organization lives in that little highlighted box, security analytics. So my team belongs to this security analytics organization, and specifically a sub-organization called the Active Cloud Defense Org. And the mission of the Active Cloud Defense Org is to counteract indiscriminate threats to the security of the AWS Cloud and our customers. So Sonaris, the team that I belong on, is a network telemetry analyzer. We analyze network traffic and service logs to identify malicious network and service scanning that's aimed at both AWS infrastructure and its customers. But some of those service logs that we use to build our system come from Will's team. So this partnership between my team and Will's is really going to be the central story of our session today. So now I'm going to hand it off to Will to introduce himself and more about his organization.
Thanks, Catherine. So my name's Will Bowditch. This week is actually my 2-year work anniversary at Amazon, so I'm super excited to celebrate that milestone on stage with you all today. Before Amazon, I did threat detection at SecureWorks, and then I was on the research and advocacy team at Rapid7. Now I find my home as a security engineer on the perimeter protection team, kind of balancing the software and security hats ever since. My org, Perimeter Protection, is home to a suite of products that help you protect your web apps from cyber attacks. I'll give a small word on each one just to give some background on the work that we do. So AWS WAF is a web application firewall that helps protect web apps from HTTP attacks like SQL injection and cross-site scripting. AWS Shield is a managed DDoS protection service that protects your web apps from distributed denial of service attacks. AWS Firewall Manager is a central location to manage your policies across your AWS resources. And then finally, AWS Network Firewall is a place to protect your VPCs by filtering and inspecting low-level traffic. So think layer 3-4. If you're using all of these services, you're golden. You get complete inline control of your traffic to protect against unauthorized access, potential vulnerabilities, and malicious performance degradation. While I know a lot about these products, I don't actually work for any of them. I work on the threat research team. It's a group at Amazon specializing in the deception and disruption of cyber threats. So the threat research team's vision is to create a virtuous cycle that accelerates Amazon's defensive and proactive security measures, ultimately making AWS an unattractive target for cyber attacks. We do this by providing first-hand, verifiable, and actionable threat data, artifacts, and indicators to internal Amazon teams on emerging threats, common exploited vulnerabilities, attacks such as DDoS and credential stuffing, and threat groups such as ransomware gangs and APTs. Our team believes that the best defense is a good offense. We prioritize the disruption of the root cause of cyber attacks where possible, such as reporting and taking down bad actor infrastructure when possible. In the same vein, rather than solely working back from today's known attack signals, we prioritize research into anomalous signals from our threat monitoring and tracking mechanisms to discover novel threats targeting the cloud. One of the ways that we discover these emerging threats is MadPot. It's a system we disclosed last September and one that I'll talk about in depth on with Catherine during this session. So to review our agenda, we're going to begin by defining what MadPot is. Next, we'll discuss the types of threat data we can harvest from MadPot and how this data enables us to disrupt botnets, stay ahead of the news cycle, and how we find new findings in MadPot data with AI. Finally, we'll explore how customers can leverage this intelligence in their own infrastructure. So assume if you're here today, you're building in AWS, you're building cool stuff in AWS, and you're familiar with diagrams like this. So your team has worked hard to make your application fault tolerant with availability zones. You're leveraging auto-scaling to meet demand. You're correctly segmented your resources with VPCs to enhance security and manageability. Now it's time to share your web app with the world, except there's a hiccup. One developer hasn't kept up to date with the latest CVEs and just pushed out a vulnerable web server to production. How fast is a vulnerable service exploited? Well, on average, within 30 seconds of deploying that server, it will be probed by another device on the internet, much like a knock on the door or a peek through the window to see who's home. We call this reconnaissance. Within 90 seconds, someone or something will attempt to exploit your server. How do we know this? How do we know this number? How is it on average 90 seconds and not an hour? Well, across AWS networks around the world, interspersed within our public IP space, we run a fleet of decoy sensors, emulating a variety of different applications and protocols. This means that when bad actors are enumerating our perimeter for your resources, they're stumbling upon and falling into our traps instead. In cybersecurity, we often refer to these as honeypots. And at Amazon, we refer to our fleet of honeypots and the intelligence system it comprises as MadPot. So before going too deep into how Amazon makes use of MadPot, let's be clear on what a honeypot is. Take the initial example of a vulnerable service being probed. Now in its place, we put the honeypot. A benign actor might send a simple HTTP request, perhaps trying to fingerprint the banner, or maybe they just fat-fingered an IP. On the other hand, a threat actor might intentionally send a Postgres client hello message, which is a different layer 7 protocol than HTTP. A simple honeypot might only have open ports without the functionality to properly respond to these requests. So you can still gather data on who's probing your server without an invitation, but this information isn't really actionable. An advanced honeypot, however, can respond to both types of requests. So it's sending a 200 OK to the HTTP request, and then a Postgres server hello reply to the threat actor. Trouble occurs when we see that bad actor, that threat actor, attempt to log in to our fake database with some random credentials. We're going to respond with Postgres in the Postgres language, hey, the credentials works, and now they're attempting to exploit with a funky Postgres query that runs a bash script, all encoded in base64 and slightly obfuscated. And these are real commands I kind of just took and changed, but these are the payloads that we're seeing. Honeypot should respond and say, hey, your query ran successfully, come again anytime. At this stage now, we've extracted the dropped payload and recorded the IP address of the threat actor. Many honeypots stop at this point, but I can say confidently that the rabbit hole goes much deeper. Because if we were to follow that chain and run that extracted dropper, it would call out to a distribution server where the actual botnet malware is hosted. And then by reverse engineering that botnet malware, you might be able to identify the puppet master, also known as the command and control or C2 server. While the infected bots conduct future attacks, it's the C2 server that orchestrates these attacks, that orders these attacks to take place in the first place. And it doesn't necessarily stop there. We could get into actor attribution, figure out what group is behind this work and what their motives are. But at this point, we now have a bunch of threat data with context that makes it actionable, and I think we can call it threat intelligence. So we have the initial scanner's IP, the hash of the dropper and the malware, a signature from the malicious Postgres server, a distribution server IP, and the identity and malware family of the C2 server. What's important now is that we don't sit on this information. The challenge for Amazon is determining how to disseminate and utilize this threat intelligence to enhance our customers' protection. So to summarize, MadPot is a global honeypot fleet that receives TCP and UDP traffic on tens of thousands of IP addresses every day. It's emulating hundreds of different services from Telnet to Postgres to RDP and then specific HTTP applications. It also mimics the fingerprints of commonly targeted devices like home security cameras, printers, small office routers, and VPS software, all with the goal of attracting and engaging threat actors, prompting them to reveal their tactics, techniques, and procedures, also known as TTPs. So back to my team's mission, this intelligence provides first-hand, verifiable, and actionable threat data, artifacts, and indicators to dozens of teams and services within Amazon. Now I'll go into one fun example as to how we use this data to disrupt botnets and C2 servers like the ones I just covered. So while we provide customers with resources to run secure applications, like all those neat services and perimeter protection, we don't force anyone to use them. Some developers may not follow AWS best practices, leading to their instances being compromised. We don't want compromised instances to be involved in attacking customers or other targets. Beyond the negative impact of the target, this can cause network congestion for AWS and its customers, as well as damage AWS's IP reputation, with Amazon IPs appearing in denial of service reports. However, having the first-hand verifiable intelligence from MadPot gives us the confidence to take strong action to disrupt a botnet's operation. So now that we've identified and verified the C2 from the previous example, we can cut off access to it across AWS networks, ensuring that even if an instance is infected, it won't receive attack commands. Furthermore, by knowing the scanners and distribution servers, Catherine's teams help us block their access to and from AWS, preventing internal infections in the first place. The threat intel we capture is critical not only for AWS and our customers, but for security of the wider internet. With all this intelligence giving us enough confidence to disrupt AWS participation in botnets, we can share this intel with the external hosting provider, the ones physically hosting the command and control servers, so they can take down the botnet infrastructure and protect the global internet. So here you can see an example of a takedown request where we provide comprehensive context, including specific attack commands observed, a hash of the malware, and the botnet malware family. This is where we fight the botnets at their source, providing direct benefits to AWS customers and the overall health of the internet. While this doesn't stop botnet comebacks, it adds frictions to their business and their operation and just ruins their reputation as an underground business. Next, we're going to jump in to a recent example focusing on a different type of problem for customers: threat actor campaigns that can lead to large-scale account customer compromise. A lot happens behind the scenes within AWS security to discover an emerging threat and get in place global protection for all customers. We use this data we gather from sources like MadPot to discover new threats and work backwards from this data to build solutions that provide broad protections. And we take these actions against threat actors on behalf of customers without them even knowing. But the thing is, we don't post about it on social media or blogs, so it's not publicly advertised. But today, I'm really happy to share one recent example, very recent, of how engineering teams within AWS Security were discovering a new threat, in this case, a VPN brute forcing campaign, and how AWS had in place global protections for customers before it even hit the news cycle. So on April 16th, the Cisco Talos Intelligence blog puts out a warning on a global surge in brute force attacks targeting VPN, SSH servers, and web app auth interfaces, emanating mainly from proxies, with this activity starting around March 18th. Then, around a week later, on April 28th, Okta raises similar alarm bells in a blog post of an unprecedented surge in proxy-driven cred stuffing attacks. Let's now turn back the clock. Although AWS didn't make an announcement on March 26th, AWS Security places its first network mitigation on actors associated with this proxy VPN cred stuffing campaign. These mitigations are, in fact, for all customers, blocking traffic from these actors at the network perimeter. Then, a few days later, on April 1st, security engineers had in place generic VPN brute force analytics that enable continuous low-latency network blocks on these actors, even when their IP address is changing. So AWS had rolled out into production all the protections which benefit all customers, from enterprise to students, more than 2 weeks before the threat campaign is hitting the news cycle. So how does this all happen behind the scenes? security engineers within AWS began noticing an uptick in VPN credential stuffing behavior using intelligent sources like MadPot prior to March 26th. Within 24 hours of the finding, engineers placed network mitigations for a series of threat indicators, like IP addresses. But IPs are ephemeral, so we know we need a more durable solution. That's where security engineers like me come in and begin working on new MadPot functionality and classifications tailored to this VPN credential stuffing campaign. So we're crafting new VPN MadPot sensors that cover a variety of services that threat actors are targeting. And we built MadPot so that we can quickly add these emulations. This then enables new generic VPN brute force analytics that gather continuous intelligence on actors who are targeting these services and blocks them at the network perimeter. This removes now the need for a human security engineer in the middle to analyze that data and choose out those IPs. All of these actions are taken without a human. So now we have low latency dynamic network blocks on actors, even when their IP address is changing. Then finally, you have intelligence gathered from these new capabilities in MadPot being fed back to the threat actor security intelligence teams. So we're generating now this flywheel effect of using intelligence to gather more intelligence, in addition to being able to learn better, more durable network mitigations on threat actors and learn more about these threat actors. Our goal is detection to protection in 24 hours. In the end, the outcome of this work led to a 96% reduction in VPN brute force attempts against AWS customers. How do I know that it's 96%? That's a question for a data scientist, so I'll hand it over to Catherine.
Thanks, Will. Up to this point, we've talked a lot about how MadPot is used to unveil critical intelligence on a lot of different things. We're tracking the activities of advanced actor groups. We're using it to place proactive protections that are in place for all customers, preventing exploitation and compromise at this tremendous global cloud scale. And finally, we're using it to systematically disrupt and dismantle botnet infrastructure across the entire internet, not just AWS. And we've made all these claims, and so far you've just taken our word for it. And Will shared kind of a staggering statistic, this 96% reduction in VPN brute force attempts against customers. So how do we come up with this measurement? How do we actually know we're making a difference? Well, as a data scientist in AWS security, I want a way to collect data and run experiments to understand how much of a protective effect are we able to provide customers with our network blocks. So once again, we can use MadPot in a very clever way to do this. You can think of it akin to a clinical trial on a new pharmaceutical. In a clinical trial, one group of participants is going to receive the new treatment, and another group of participants receives simply a placebo. So what we do is we deploy multiple fleets of MadPot, honeypot sensors, and these are akin to these same clinical trial groups. One group is going to be protected by our perimeter network security controls, which is fed by our analytics, and a separate fleet gets no protection at all. So this allows us to compare MadPot interactions that lie inside and outside our network perimeter. So the great thing about this is the protected and unprotected fleets are subject to the exact same cloud scale threat landscape. They're experiencing the same actors out on the internet. And a threat actor doesn't know if the host they've encountered is a part of a protected or an unprotected fleet until they attempt the connection. So let me give an example. So here on this slide, we have two threat actors at the very top. Threat actor 1 is not being mitigated by our system, where threat actor 2 is being actively mitigated. Beneath that, we have two separate fleets of MadPot, honeypot sensors. The first one is the unprotected fleet, and the second fleet is this MadPot protected fleet, which gets the benefits of our network security protections. So in this scenario, threat actor number 1, which is not being mitigated, is allowed to freely connect to MadPot sensors in both the unprotected and protected fleet. But threat actor number 2, which is being mitigated, can freely connect to MadPot sensors in the unprotected fleet, but when it attempts a connection to a sensor in the protected fleet, that connection is blocked. So let's tie this back to the example that Will gave for VPN brute forcing campaign. So in that scenario, by using the protected and unprotected fleets, we were able to directly compare what happens to an exposed VPN service outside our perimeter network protections versus inside. And specifically, we're comparing the difference in how often threat actors attempt to exploit a decoy VPN service, which is unprotected, versus those who have the benefit of our network blocks. So this is the way that we construct split testing groups to do A/B testing to measure with statistical rigor how much of a protective effect we provide for our customers' services. But the thing is, we do this for all sorts of threat activity, not just VPN brute forcing. And so what we end up finding is across all classes of exploit types that we track, our perimeter protections result in 80% fewer exploit attempts for our customers. Now, AWS has a goal to make the AWS Cloud the most secure cloud computing environment. So you can see from this statistic, yes, we have areas to improve. But what's great about this A/B testing framework and these corresponding fleets of protected and unprotected honeypots is we're able to precisely identify where those areas for improvement are, whether it's a specific service or a certain type of exploit activity or actors from a certain botnet family. And the idea is that we're going to go ahead and focus our research and development on those areas so that we optimize our analytics and our network mitigations and research to ensure that we're going to maximize the protective effect we have for our customers. But what I want to emphasize is a critical part of this entire system relies on the fact that we can have high confidence that the traffic that we are blocking is indeed bad. So we've built this broad protective effect, a first line of defense for all customers, but it's not magic. So we will continue to strive to make our system more effective against threat actors, but you as a customer, don't let your guard down. It is still imperative that you secure your workloads in the cloud. All right, so now I'm going to switch gears and talk about some ongoing research in AWS security. So far we talked a lot about how we're able to classify and detect threat activity from a lot of classes of threat behavior we already understand fairly well. Things like botnet self-propagating malware or already published repositories of vulnerabilities and CVEs. But the thing is, new exploit signatures are going to crop up all of the time, or a new exploit is leveraging a previously unknown vulnerability. So in the example that Will shared on VPN brute forcing, we talked about how there was still a security engineer in the middle, in the very beginning, that's knee-deep in data, who's scratching their head and turning over stones to uncover this interesting piece of intelligence that we then quickly action. But within engineering teams at AWS Security, we know we need to understand how to scale this threat discovery process. And this means that if we can effectively scale this, we can identify novel threat intelligence faster and then rapidly build it into the protections that we have in place for customers. And to do that scaling process, we will use machine learning and AI. So using machine learning and AI, we're going to process the over 700 million plus interactions MadPot observes each and every day to uncover emerging threat activity and integrate these findings directly into protections for customers. So our immense scale gives us an incredibly unique perspective to observe the global cloud threat landscape, and we can use this to discover new and interesting threat behaviors before customers can for themselves and before it hits the public domain or news cycle. So now I'm going to go through at a high level an example of how we can use AI and MadPot to maximize the threat intelligence discovery process. So in this example, we have an incoming interaction to MadPot. And an incoming interaction, we get all sorts of metadata. We get the IP address the interaction comes from, the port and protocol where the interaction occurred, information about the payload. And what happens next is MadPot is going to attempt to classify that interaction as something it already knows. But sometimes MadPot observes something that it's not quite sure what it is. And sometimes this can represent interesting and novel intelligence that we want to know how to action. So what do we do in these scenarios? Well, the idea is we want to create a sort of map, a map that is informed by all of the historical interactions that MadPot's ever observed. And within these maps, in this map, we are going to group together interactions that represent the same family of threat behavior. So in this case, we have a collection of yellow dots marked as class B, and then a collection of pink dots marked as class A, and you could think about those as being two different types of distinct threat behavior. So the idea is when we have a new incoming interaction to MadPot that we're not sure how to classify, we simply figure out where does it live on the map. And we look at whose its neighbors are to better understand how do we action this intelligence and what should we do to protect customers. So in this case, our incoming interaction looks a whole lot like it belongs to the threat activity of class B. So how do we actually construct this map? So what we need to do first is take all of the historical interactions that MadPot's observed, and we're going to pipe it through a machine learning model, in this case a neural network. but the output of the neural network is not a prediction of good or bad. It's not of cat or not cat. In this case, the output is the map. And we call this thing a learned representation. So you can think about it of like a projection in lower dimensional space where all of these kind of high dimensional features within MadPot are mapped into such a space where similar types of threat activity gets grouped closely together. And the idea is once we have a model that knows how to make the map, we know how to do a mapping. So when we see a new interaction that we're not quite sure how to classify, we simply pass it through the exact same machine learning model, and we take the map that we've created with all the historical interactions on MadPot, and we figure out where does that new interaction lie on the map. And then we'll do secondary analysis to better understand what sort of threat behavior is this interaction and use that to figure out how to action it to protect customers. All right, so now we're going to transition into kind of our final section, which is about maximizing the benefit of MadPot in your own infrastructure. So up to this point, we've talked about how my team and Will are data mining all of the logs we're getting from these global honeypot fleets to build a first line of defense for every customer, but it's just built off of the data we're collecting from our honeypots. So you're probably wondering, well, what about when there's activity happening within my own infrastructure that aligns with the intelligence that we are gathering in MadPot? And the answer is we do have a few ways to vend you that intelligence through other services that AWS offers. So first up is how MadPot intelligence integrates into AWS Web Application Firewall, or WAF. So within WAF, there's a number of these Amazon managed rules. So I have the list shown here, and specifically the highlighted one, this Amazon managed IP reputation list. MadPot intelligence feeds directly into this rule. So you as a customer can enable this rule to protect your web application from the exact same threat actors that we are observing exploit services in MadPot. So you can recall from that VPN brute forcing example that we aim to rapidly and respond within like 24 hours, this idea of detection to protection in 24 hours. And that includes pushing signatures to WAF. So as a customer, I really urge you to enable this rule, but really any of the rules within this Amazon managed rule list. For example, that AWS managed reconnaissance list, that's something that my team Sonaris also publishes to. But the idea is there's a lot of work being done behind the scenes at AWS Security to find intelligence and publish it to these rules that you can then benefit from as a customer. All right, so next up is MadPot intelligence in Amazon Guard Duty. So MadPot vends intelligence to Guard Duty. So if you enable Guard Duty, you can receive MadPot intelligence findings and alerts. And in fact, MadPot intelligence informs a number of different finding types in Guard Duty, but I should mention that MadPot is not the only intelligence source that feeds Guard Duty. They're getting data from lots of different places, including MadPot. So in this example here, we have two different finding types. On top, we have this EC2 command and control activity finding type. That's one that MadPot informs. And then beneath that, we have an EC2 Bitcoin cryptocurrency mining finding, also something that MadPot intelligence informs. So as a Guard Duty customer, you can configure remediation steps for these specific finding types. And if you aren't already enabling Guard Duty within your infrastructure, I think you can enable it for free for the first 30 days and analyze its value for yourself. Okay, now we're coming full circle back to the shared responsibility model. So what we've shared today are the ways that teams like my own and Will are raising the bar on the security of the cloud for you as customers. We're allowing customers to get higher level services plus our security services, and you're going to get more and more for free. And in this presentation, we've shown how we're using the global scale of intelligence we're deriving from MadPot to place perimeter protections that benefit all customers against emerging indiscriminate cloud scale threats. So by doing this, we're effectively removing the noise floor of internet noise, allowing you as a customer to focus on your own unique security posture. And then finally, in this last section, we covered ways that you as a customer can use other services within AWS, namely WAF and Guard Duty, to consume MadPot intelligence as it relates to activities that occur within your own infrastructure. So as a takeaway, I challenge you to walk away and explore MadPot in these other services to dig deep into understanding your own unique security posture. All right, that's all we have for you guys today. Thank you so much for attending our session. Once again, thank you for attending our session.